Welcome to Topic 9, Structural Connections and Interfaces. Structural connection being put something together and very strong. An interface being something you put it together, but you can take it apart, on and off. Both of them, the mechanics of the design of these types of connections, similar. You have to meet a structural or physical strength or stiffness requirement, and or when you put it together, it's either going to be aligned afterwards and then tightened, or when you put it together, it's already aligned and then you attach it. There's various types of these types of joints, from the structural, bolted, welded, pinned, to couplings, toothed couplings, magnetic couplings, contact to non-contact. We're going to be focusing on mechanical contact joints in this particular topic. The first thing you want to do is visualize your joint. What must it do? This is part of establishing the functional requirements, the specific functions it must do in terms of strength, stiffness, repeatability. Play the movie in your mind of how things move. You may create a beautiful solid model or picture of your device, and if it doesn't move, it just sits there. That doesn't do you any good, right? So you will have to either animate it on the screen, or I like to, especially during the early phases of design, learn to play the movie in my head. Okay? So for example, how did Hoberman come up with the idea for his spheres? For example, if you look up here in our collection, I happen to have one up here. Now, the reason I'm walking over here to do this, as opposed to having it staged over there, this is all part of the visualization part of this course, Exercise in Life. Keep your room, your design area, full of stuff. So when the idea hits you, you can walk over and hopefully it exists somewhere and you can expand your knowledge. Pretty cool, huh? What kind of brain was thinking of this thing and what was it doing when that happened? I wish I knew. Now, interfaces also have an interesting function. And look at this scissors. And remember from topic 4, we talked about scissor linkages. When this was fully collapsed, all the links were here, opened up, and then pull it back to close it, but it didn't close all the way. Why did it not close all the way? And that was because of little gaps between the joints that are there, so enable you to be able to build it in the first place. Look at, for example, here's a red plate with these two green plates to be bolted to it. As drawn, one of these green guys fits and looks like there is a space for the bolts to go through, but one of them has a little bit of red showing. Why is that? Well, when the plates are properly, perfectly aligned, if the holes weren't drilled in the right place, they may not line up. To make the holes line up, the plate may have to be skewed, which would never allow you to actually bolt the parts together in the orientation you desired. This is part of the error analysis of a system, or tolerance analysis, that we must do as machine designers or designers of any type, where parts are put together. You have to look at every dimension where they're required to interface, and if each of those dimensions is off by a little bit, is there still a geometric condition where they will come together and even be able to have all the fasteners engage, such as here, and allow you to be aligned, such as shown over here on my right. To ensure that you get alignment and all fastening points engageable, you often will have to vary the tolerances on your dimensions. So think about an automobile engine and all the different parts and bolts and holes and everything that has to go together in order for the engine to function properly. That's a big part of what engineering is all about. It's not just, oh, I have this creative thought, oh my goodness, oh, it's wonderful. But, okay, now how do I actually do it such that it's robust and I can make it again and again and again so I can make money? So let's look at structural joints as a starting point. We're going to be looking and considering riveted, bolted, and welded joints. We'll continue later with adhesive. And the advantage and desirable point of a structural joint of riveted, bolted, or welded is that it's a mechanical connection. The mechanical connection is either by a rivet that is like a pin that goes through holes and then is expanded to fill the holes, or a bolted joint where the bolts go through the hole, but there's typically a little bit of clearance. And the bolted joint holds by squeezing together, and then the joint is held by friction. Whereas remember, the rivet, when it goes in and expands to fill the hole, now can take loads purely in shear. And then welded joints, where of course the metal from the two parts are fused together by heat. All three of these types of joints are not just for metals, also plastics. You can weld plastic together. You can bolt plastic parts together, and indeed you can also rivet, even with plastic rivets, parts together. The design of these joints enables you to consider the part, if it's done properly, as if it was all out of a solid piece of material, but allows you to then take discrete pieces of material that should be cheaper and easier to make than trying to do the whole thing at once. Now, one of the things we want to consider when we're welding structures together, manual, automatic processes, and the design of the part edges in order so they can be welded properly to achieve the proper strength. In welding of the material, you have to also be very, very careful of, you may specify a high strength material. Weld it, and then you can lose a lot of the strength of the material. Why is that? A lot of materials achieve their strength by heat treating. When you weld them, you raise them very hot, and then they're quenched by the air or the material around them, and you change the state of heat treat of the material. So be very, very careful if you're specifying a welded joint, what that does to the strength. Different types of welding from, this is a TIG welder here, tungsten inert gas, where the operator with a great deal of skill, or it can actually be done robotically also, tungsten electrode arc comes down with a shield of gas. And now you see what happens if things creep and let go. We'll get to adhesives in a minute sometimes. Spot welding, which is where many, many welds in cars are made. And conventional arc welding, all options. And there's many types of conventional arc welding. Submerged arc. If you look, for example, at giant towers, welded by a process called submerged arc welding. And these tend to give you very beautiful welds over very long distances. So consider how you design a welded structure or welded parts. This little case study here is from a sprocket that had to get welded to a squeeze type coupling that could be attached to the shaft of a motor such that the system would then drive a chain. And this is from a first robotics machine from some years ago. What the spreadsheet is showing, and you can read in the text, is the red part here represents the weld. The weld is only on half of the coupling, because if you were to weld all the way around the sprocket to the coupling could not function in the squeezing clamp type mode. See, back on the back side here, it acts like a hinge. And so one half of the coupling has to be able to close to clamp. So now you have an asymmetric weld with the radial load from the chain force. Is that enough strength in that weld to handle that chain force? You could say, design it in solid modeling, run your final analysis, and see if it works. And it may work. But if it doesn't work, then you have to think, oh wow, what do I have to change? This is where the value of the real engineering happens. You do the closed form analysis to write the equations and then implement them on the spreadsheet or MATLAB, what have you. So it allows you to very, very rapidly play what if. What if I make this bigger, smaller, change my loads? You can think very rapidly, and you can also tend to see the trends of things and what they're happening. That's why the whole world is not just do a final analysis. So that's a good final check, but not necessarily for your initial creative exploration of the space and sizes. Now, adhesive joints, and as we just saw earlier, my little penguin friend decided to take a dive. And we had stuck him up here earlier with a bunch of tape. And tape, when done properly, doesn't let go. When done not properly, will tend to slowly creep and boop, fall off. You can see them slowly moving there. If you're going to use an adhesive, you have to pick the proper adhesive for the job. There are many epoxies, acrylics, that will hold and hold and hold. And other ones, particularly when it's warm, will start to ooze. Or what happened with this guy here, and you can say, why is it holding here but not there? With adhesives, often the most critical thing is your surface preparation. How clean is the surface? In this case, this is cloth, and I'm sticking an adhesive to the cloth, but there's a lot of dust and lint on the cloth, which dramatically weakens the joint. There are plenty of applications where adhesive can last, for example, with cloth, for a long time. There's actually forms of alternate forms of attaching pieces of cloth using adhesive tape as opposed to stitching. Adhesives are used in structural panels. Here we have metal, plywood metal to make a form of a composite. Here is where rubber was bonded to the surface of a cardboard wheel to try to make a tire, and it came off. Bonding rubber to other materials can often be very, very difficult unless you get the right adhesive. Many different types of joints. What to use depends upon the strength that you need and also the manufacturing costs. Machine tools often make extensive use of adhesives between elements to hold them together so they don't have to be precisely machined. They can be good enough, brought together and glued together, but the positioning is then established with the fixture until the glue hardens. So I use adhesives in quite a lot of the machines and structures and products I design. And how do you determine, do you use a bolt versus an adhesive versus a welded joint? Well, you keep all of those parameters of the different types of joints in your brain. And when I do a design, I often will design it for all three. And then I do an assessment of cost, talk to the manufacturing people, what do they think is the best thing to do. And then quite often also we'll build 2 or 3 test parts. And not only just the perfectly made ideal condition part, but when I make that part in normal manufacturing mode, can I get it clean enough, for example, to be strong enough? Now, bolted joints, if you think about what a bolted joint's function is, to hold one part to another, there are so many different functions you may call upon your bolted joint to do, which is why there's so many different types of bolts. So for example, a classic bolt and nut, but for here a polymer has been added such that when the nut is tightened on the bolt, it deforms the polymer between the threads and you get very, very high static friction. Dynamic friction is low enough that you can tighten it, but when you let go of the wrench, it locks in place. Anti-vibration, for example. A plain nut, or what's called a lock nut, which has a plastic insert, again, to provide that extra bit of static friction when you come to a stopping point in tightening the bolt such that it won't vibrate loose. And remember, polymers, it's not just the static friction. What you're really getting there is because pressing hard on it, it's giving you damping at that interface. And that's very valuable to help prevent loosening under vibration. This type of bolt here is called a shoulder bolt, often used in linkages when you want to attach one link to another through a pin joint. The shoulder can then have a nylon sleeve on it to act as a bearing, or if the loads are modest, you can just have the shoulder itself on the shoulder bolt act as the pin for the bearing joint. A really good thing to do is get a catalog from one of the many companies that supply machine parts. Look through all the bolts. Go to a do-it-yourself store, to the fasteners aisle. Wow, boy, they got a lot of fasteners. Pull the drawers out, look at them, play with them. Remember, the tactile feel of how things work is very important for wiring your brain. ask yourself the question, why are these threads this way? What's going on with this bolt head? Why are sometimes I'm using a hex head? Why am I sometimes using an exterior hex? So in other words, a socket head, sometimes Allen screw, or just a regular hex head bolt. Why would I use one versus the other? This type of bolt, of course, you can put in a counter bore so it's flush with the surface. If does not a matter to you, then just a regular hex head bolt is usually what's used. Now, the mechanics of bolted joints. You sometimes look at a part, particularly a large machine, and you see a lot of bolts. Why, when I'm looking at, for example, a pipe joint flange, do I often see so many bolts all the way around? This gets back to the function of a joint. In this case, where I've got the flow of a fluid through the joint, the functional requirements are the joint has to seal and it has to be strong. For there to be loads on the pipe, it has to resist that. The bolts themselves will not seal. There'll be some sort of either a gasket or O-ring inside the joint. And even if it was a metal-to-metal joint, which is rare, any kind of seal then relies on even pressure. And remember St. Vinay's principle from Topic 3. Now look at the cross-section through a bolted joint and consider when you push on it, you push on that joint by tightening the bolt, and hence essentially squeezing the joint. If this bolt diameter is D, when I go 5D away from the joint, no matter how hard I tighten that bolt, I really won't be able to detect it over here. Come away about 3D, and I'll still really won't feel it, but I may, it depends on the thickness of the joint. And what happens is that right under the bolt head, you start sending out influence. And this angle here, in the worst case, when you're trying not to have it bother you, is 45 degrees. If you're trying to design on a joint to not leak, then I do the more conservative 30 degrees. These are the stress cones that emanate out from the bolt. And when I have to have a joint that must not leak, I'll put enough bolts such that the stress cones overlap. I want my stress cones where this is, if I drew this as 30 degrees, that's a very large value of 30, to overlap. How much? Just overlapping at 30 degrees, because in reality it's probably a little closer to 35 or so, and then you'll get the overlap. What happens then is whatever seal you have in here, like a gasket, is then feeling pressure from the bolts to joint everywhere. That becomes very, very important. Everything's falling. So things don't fall apart. If the gasket is preloaded by the joint pressure, and there's a period of the gasket that doesn't have any joint pressure, the pressure in the pipe then can act to tunnel its way through, and you get a leak. Remember, everything is a spring. A bolted joint is also a spring. There's a certain stiffness of the flange. There's a certain stiffness of the bolt. We can model this. And now, in modeling that, we can come up with how tight do the bolts have to be in order to keep that joint always in compression, even given variance of forces applied on the joint, either external forces or from pressure variations. And our job is going to be to always keep that joint preloaded, always in compression. Those springs should never be allowed to extend and come loose. And furthermore, when I design my bolted joint in the context of looking at the springs, I can figure out how tight do I have to tighten the bolt such that when the interior pressures or forces acting the joint happen, the alternating stress seen by the bolt is low enough that I will not fatigue that bolt with time. All this is covered in the text. Make sure you're familiar with how you do that calculation. Very critical. Now, with respect to the stiffness of the joint, if you're designing a machine, where I'm looking at not just the axial stiffness of the joint, but for example, in a piece of machinery like this, this is a clamped joint. There are different parts that are bolted to it, the structure. How do I know, for example, when I bolt a beam to the wall, it acts like a cantilever beam, how stiff that is? Imagine that I had a wall and I had a beam, a wall or the column of a machine, and I had another structure bolted to it. And something else is happening outside of the end of this machine. And when I'm designing my machine under load, I want to make sure this beam doesn't deflect too much. How do I do that? Well, I'm going to have the deflection of the beam, assuming it was rigidly anchored at the wall. So this is your deflection equals F L cubed over 3EI. This being the modulus elasticity of the beam material, and I being the moment of inertia for the cross section of the beam. But I'm also going to have the fact that back here this looks like a spring, and this looks like a spring. And now I've got these springs with a long lever arm, and this spring is going to compress, and that's going to extend. The springs are spaced some L apart. So I'm going to have an angular motion due to this spring motion at the base. So the same type of analysis in terms that you would do to calculate just the axial stiffness of a bolted joint applied to these 2 points is now used to determine the deflection at the top and the bottom, and hence you can figure out the tilt of that joint. Look here at this finite element analysis of a joint that has a bolt applied, and here are the stress cones. See, they come in, and it's a little bit of ambiguity in terms of where does this stress cone start and what does it angle in at. That's where the 30 degree is a conservative number, 45 degree, it's definitely all the area of stress is included, or strain in this picture we're showing. The next thing is, when you design a joint, you can design it such that it leaks before it breaks. This again gets back to understanding how the state of stress in the bolt changes, particularly with time and things fatigue. Leak before break is the most often applied criteria. You'd rather that something opens up and the bolted joint stretches, then starts leaking, rather than stress is applied and it's so high that bang, all the brakes bolt, and then you have a catastrophic failure. So you want to avoid catastrophic failure. Now here's a little bracket case study building on this first picture I showed here. And of course the spreadsheet that goes with it that I invite everyone to take a peek at and look through. And what this spreadsheet does, and you can't see here from this eye chart, but what it does is it takes the cantilever length, the load, the type of bolts you're using, the bolt forces, calculates the stresses, looks at the wall itself to which you're bolted into, and how is that wall deflecting, such that the total stiffness is the stiffness of the wall plus the bolts, and comes up in the end with what are the stresses in the bolts, and will the bracket be able to hold the load with the stiffness that you want. I would suggest, as a really excellent learning opportunity, that everyone thinks about the problem, develops the analysis themselves, writes your own spreadsheet, for example, and compare the numbers. Use something that you find or are given. Always do some checks by yourself to make sure, yeah, that seems to be in the neighborhood, before you dive into using a tool. Now, if we are to do finite element analysis of a bolted joint, how do we do it? In particular, for getting the stress in the joint and the stiffness. So here we see a column. This is a circular column with a bolted flange base. And the question is, we want to use finite element analysis to help us determine how many bolts to use. Because the requirement in this for a machine tool column is not that it shouldn't leak down here. There's no fluids going through the center. But then when forces are applied, it's stiff enough. Do I use 3 bolts, 6 bolts, 12 bolts? The management person in you would say, we have to minimize cost. You can use 12 bolts. That's very expensive. Why don't you just use 6 bigger bolts? Now, looking at the base here, why do we have these overlapping circles? What these overlapping circles are based on from doing a solid model of the machine and then doing a finite element analysis is the following. If you design a part in a solid model, and then you take it and you say, aha, this part is going to be bolted to this part. Great, let's now finish the solid model, the assembly, and we'll take it into FEA and apply a load, and we'll define the modulus elasticity here and here, and run the finite element analysis. Well, the finite element analysis is not smart enough to know exactly what you're doing. It's going to essentially act like all these surfaces are knitted together. In a more advanced modeler, you could specify this joint in here as what's called a gap joint. It can open but not close. Then what you would have to do is apply forces around the joint to emulate the bolt forces. That is one, for a more powerful finite element tool, way you can do this. If you're running a very simple modeler that won't necessarily do this gap opening elements, this is a nonlinear form of analysis, you can use the notion that I understand what the stress cones are, and when I have my bolted joint in here, if I only have 3 bolts, that the stress cones are effectively going to lead to an area of contact that's this circular area under the bolt head. And that's what's represented here, where I've made these little islands or mesas, because when you've only got 3 bolts and this flange or this column with this flange is bolted to the base, and the bolts are tightened, those stress cones expand out and really only have good intimate contact at 3 points at those 3 areas. That area is based on this stress cone diameter. Hence, with 6 and at 12, they actually all overlap. And what this finite element analysis is showing us on a relative basis, excuse me, that the 3 bolts give me an average of, for the load that was applied here, 16 microns of deflection. 6 bolts gives me 14 microns of deflection, and then the full 12-bolt array gives me 13 microns of deflection. Is that a lot? It depends upon what your machine was intended to do. It seems to me that the biggest gain goes from 3 bolts to 6. There's not that much added gain when you go from 6 to 12. The reason you'd use 12 is because if you had a sealing function also. If you didn't have a sealing function, the 6 bolts should be plenty. But again, you can run the numbers and determine exactly what if what you're getting is what you need or not. Now, when would I rivet something versus bolt it? Well, rivets can be very easily applied and are much cheaper than a bolt in general. You can apply a rivet through a blind hole. That is, you can have two parts together, drill the hole, put the rivet in, rivet it without having to get access to the backside. Rivets also have the ability, if the holes aren't perfectly aligned, they expand and they will fill the material in the holes. Bolted joints, remember, they work by clamping together. So when you look at a riveted joint, so first of all, let me go back to my bolted joint picture here. Here's the bolt head, bolt shaft. You will always have some clearance between the shaft of the bolt and the bolt hole. And if I want to keep one part from slipping against another, it's by compressing the two, then the force in the bolt times the coefficient of friction is that then what gives this joint, the bolted joint, a resistance to sliding. You're not relying on clearance between the shaft of the bolt, or the shank, and the hole. You're not relying on there being zero clearance, and therefore it'll take a shear load. Because when you have a lot of bolts and a lot of holes, they can't all simultaneously engage the parts to have zero clearance. They only can all simultaneously clamp, and then together the summation of their clamping force with the coefficient of friction prevent the joint from shearing. Rivets, on the other hand, are designed such that, this is what's called a pop rivet, when this ball, which is attached to this shaft, is pulled, it expands the metal of the rivet to fill inside the hole, and it's pulled and pulled and pulled until bang, it breaks, hence the little pointed part here. And the stem of the rivet breaks off and is discarded, and you have a nice, neat riveted hole that has expanded, riveted joint where the rivet has expanded to fill the clearance in the hole. The hole can't be arbitrarily large, it won't expand to fill it. So if you keep within tolerances, you'll be just fine. Now, why did I include pinned joints in addition to riveted joints? Well, a pin joint, and there are several types of pins, operates on the similar type of mode where the pin resists shear of the joint. In this case, a dowel pin will be pressed into a hole. A spiral pin or a slotted spring pin are pressed into a hole, but the spring has radial squishiness, radial spring, such it can accommodate to fill the hole and often slightly misaligned parts. So it acts like a Lego in terms of elastic averaging between the receiving end and the pins. So when you put a pin joint together with one of these, or a collection of spring pins, the joint will feel tight and each of the spring pins will withstand shear of the joint. Lastly, rivets. These are blind rivets, these pop rivets. There are also rivets that come from each side of the part. There are also hot rivets. When you drive across some old bridges in particular, you see there are just lots of rivets everywhere. It's not necessarily an old technology that, oh, who would ever use them anymore. If you look at airplanes, there are just thousands of rivets all over, hundreds of thousands of rivets on your typical large airplane. Very, very powerful, fastening tool. Next, we'll come back to structural interfaces, where we're looking at interfaces that come together and go apart.